you can hear me?
Yep, loud and clear.
Okay. So hi everyone, I'm Qian Hu from University of Glasgow. I will present our recent work on the waveform difference and waveform accuracy. So we proposed a new approach to evaluate the gravitational waveform model accuracy by looking to the difference between two waveform models. And this method is free from the unknown true waveform or numerical relativity simulations. And we have applied this method to the latest catalog parameter estimation samples to see if any problematic waveforms are used in data analysis and its possible impacts on parameter estimation. We also try to see the good and bad regions in the parameter space. Also, we try to make predictions for the waveform accuracy requirement for the future high NCR detections. So let's first look at the theory. When the waveform models will always have some errors compared to the real waveforms. But as long as the detector cannot distinguish it from the real one, we can say it is accurate enough. So to quantify this, we can construct such a waveform family. It's a combination of the real and model waveforms with a parameter lambda ranging from 0 to 1. So distinguishing the waveforms is equivalent to measuring the lambda. So if the error of measuring lambda is greater than its domain of definition, or you can say the parametric distance between the real and the model waveforms, we can claim that the detector cannot distinguish the two waveforms. So the model is accurate enough. This error can be obtained by Fisher information, which is the inner product of the waveforms error. So we call it the length of the error is smaller than 1. It shows the waveform error should lie within a unit ball in the inner product space. Note here is an inner product space, so we can use any properties of a general inner product space, like we treat waveforms and their errors as vectors here, and we define their length. So I put the equation we got just now. There's a problem is if we want to calculate delta H, we need to know the real waveform, but the fact is we don't know. We usually use the numerical relativity simulations as the real waveform, but it is really expensive to calculate, and the number of our simulations is very limited. There are some regions in the parameter space are not covered by the NR simulation, so we cannot calibrate the waveforms or evaluate the errors in those regions. To solve this problem, we introduce another waveform model, H2. And although we don't know their errors, delta H2 or delta H1, but we do know their difference. The difference between waveform errors is just the difference between models, because the real waveform is canceled. So we define the waveform difference as delta here. If we assume the two waveform models are both accurate enough, and using the triangle inequality, we've got this, the length of the waveform difference should be smaller than 2. So if we find a violation of this inequality, we can say at least one of the waveforms is not accurate enough. So let's look into it. So even though we have got the length of the waveform difference, there are still many possibilities as plotted in the different line styles. So let's first look at the case 1. If we got the delta longer than 2, here the black circle is a unit ball of radius 1, and blue vectors are the waveform errors. And so if their lengths are longer than 1, longer than the radius, then it will be out of the black circle, so it is not accurate enough. If it is within the circle, it is accurate enough. So now the waveform difference, the red vector, is longer than 2, is longer than the diameter of the black circle, so we cannot put it inside the circle. There must be 1 or 2 sides of the red vector that are out of the black circle. So maybe there is only one waveform is not accurate enough, as the solid line shows. Maybe both of them are inaccurate, like the dashed line shows. Okay, so what if we got the waveform difference less than 2, as is shown in case 2? And unfortunately, everything is possible. Maybe both are accurate, as the solid line shows. Maybe both are inaccurate, and maybe only one of them is inaccurate. So the key idea of this method is if two waveforms have significant difference, they cannot be both accurate enough. At least one of them is seriously deviated from the real waveform. So, but if they are making similar mistakes like here, we cannot examine it in this method. So this method can be extended to the detector response or the detector network. We can always construct a quantity that has upper limit of 2, which is shown in the box. These are equations that we're going to use. So now let's go to the applications. We know we used 2 waveform models, one from IMR family and one from EOB in the latest analysis of the gravitational wave catalog. And we mix their posterior samples together to eliminate the systematic errors caused by the waveform error. So we first apply this method to the parameter estimation samples to see if any problematic waveforms are used in data analysis. So for each event, we calculate the mean and median of the waveform difference, which is shown in the left panel, and the fraction of delta less than 2 samples, or we can call it the good samples, although they are not necessarily good. The fraction of good samples shown in the right panel. So you can see for most events, we have the mean or median of waveform difference less than 2, and the fraction of good samples over 60%. But none of the events has all samples passed our assessment. So here the plot shows the bad samples mainly come from the low mass ratio region or high spin region. Here each subplot is an event showing the delta's distribution in the parameter space. We have mass and spins. So we can see the yellow points, the bad points, are denser at the low mass ratio region or high spin region. It means the waveform accuracy becomes worse in those regions, and sometimes they cannot pass our evaluations. At least one of the waveform model is inaccurate. And using the property that the waveform difference is proportional to SNR, and compare our current SNR and the future third generation detectors SNR, we can make predictions for the future waveform accuracy requirements, which shows the mismatch between the model and the real waveform should be improved by at least 3 orders of magnitude. This is consistent with previous works, but what we can tell you here is the improvement should be even larger in the high spin and low mass ratio regions, and those regions might be where our simulations are most needed for the future. So at last, we investigate the relation between the waveform difference and the consistency between posterior samples generated by different waveforms. We calculate the Jensen-Shannon distance between the IMR and EOB posterior samples. Here, the larger distance means the less similarity between 2 samples. And the distance is defined for one-dimensional samples, so we choose the maximum just distance in these 4 physical parameters to represent the inconsistency. We can see when the fraction of good samples is less than 40%, the GS distance will be larger than most other events. Yeah, of course, we know the waveform difference is not the only factor that can influence the posterior consistency, but this plot shows at least when the waveform difference is large, it is more likely to get inconsistent estimations from 2 waveform models. So the time is up, so I'll just put summary here for you to read. And we have more results than what's shown in this presentation. If you're interested, you can check out these 2 documents. And that's all for my presentation. Thank you for listening.
Thanks very much, and apologies for missing your 2-minute warning. I was so engrossed in the talk. There are no questions yet in the Q&A, but people do feel free to ask them. One question which I have is, so you worked out the waveform difference between two different models, between SEO BNR and IMR Phenom P. Would there be any benefit to introducing a third waveform family to the mix? So, for example, one of the NR surrogate models, which are around these days.
Yeah, that's a reasonable thing to do. We may get some new information about the waveform models by comparing different pairs. So that is possible thing to do. But the worst case is all the three models are making similar mistakes, so we cannot get any useful information. That is the worst case.
Okay, yeah, that seems reasonable. Well, if anybody else has any questions, then I suggest you ask them on the Slack channel, and let us move on to the final talk before the break, which is